All right, so we're going to move on to the next example where the directions ask us to find the area of the region R in the first quadrant that is bounded above by y is equal to rad x and below by the x-axis and the line y is equal to x minus 2. Okay, so again, we want to draw a graphical representation of this. Okay, so y is equal to rad x. That graph is going to look like so. And then y is equal to x minus 2. That graph looks like that. So we're told our region is in the first quadrant. Okay, so our area is going to be the area that we have in black. Now, this is going to be a little bit different and a little bit more difficult. This is like more along the lines of like a test question than what we've seen in the other examples. Okay, and what makes this more difficult is when we look at like the function here, the function that bounds this area from above is always that curve in dark blue. Okay, it's the function y is equal to rad x. But when we look at the function that bounds the area from below, that changes because between the x values of 0 and rad 2, or sorry, 0 and 2, the function that bounds the area from below is the x-axis. And then between the x values of 2 and 4, the function that bounds the area from below is that line. So if we want to compute that area in black, we actually have to break the integral up into two integrals. The first one is going to calculate this area here in green. And the second one is going to calculate the area in red. Okay, so if we want to set up an integral expression to calculate the area in green, we're trying to compute the area between the curve and the x-axis. So we're integrating from 0 to 2, just our function rad x, which we are integrating with respect to x. To that, if we want to compute the area in red, that's going to be the area enclosed by the two curves. Okay, so the function that, well, first off, our limits of integration, the lower limit is 2, the upper limit is 4. The function that bounds the area from above is rad x minus the function that bounds the area from below is the function x minus 2, which we are integrating with respect to x. Okay, so we're just going to go ahead and work through to compute the value of this integral. Okay, so the antiderivative of rad x, or x to the 1/2 power, is x to the 3/2 divided by 3/2. So dividing by 3/2 is the same thing as multiplying by 2/3. And then to that, we're going to add the antiderivative of rad x, which again is 2/3 x to the 3/2 power, minus the antiderivative of x, which is x squared over 2, plus the antiderivative of 2, which is 2x, and then we're going to evaluate that at 4 and at 2. Okay, so when I do this, when I plug 2 in, the square root of 2 is 2, 2 cubed is 2 rad 2, times 2/3 is 4 rad 2 over 3. Minus, when we plug in 0, we get 0, plus, and then when I evaluate the next antiderivative at 4, 4 to the 3/2 power, the square root of 4 is 2, 2 cubed is 8, times 2/3 is 16 over 3, minus 4 squared, which is 16 divided by 2, which is 8, plus 2 times 4, which is 8, minus, and then when we plug in 2 to the 3/2 power again is 2 rad 2. When I multiply that times 2/3, that's 4 rad 2 over 3, minus 2 squared is 4 divided by 2 is 2, plus 2 times 2 is 4. Okay, so just to clean this up, we have a positive 4 rad 2 and a negative, positive 4 rad 2 over 3 and negative 4 rad 2 over 3. Those cancel. Negative 8 and positive 8 cancel. So that leaves me with 16 over 3 minus negative 2 plus 4. So negative 2 plus 4 gives me 2. And 16 over 3 minus 2 is 16 over 3 minus 6 over 3. So we get that area to be equal to 10 over 3. Okay. Again, pretty complicated. We have to set up 2 different integrals for that. Okay, so I want to talk about this next. So it says some regions are best treated by regarding x as a function of y. And it says if a region is bounded by curves with equations, x is equal to f of y, x is equal to g of y is equal to c, and y is equal to d, where f and g are continuous, and f of y excuse me, is greater than or equal to g of y for all y in the closed interval from c to d, then we can compute area with respect to y as well. Okay, so when we look, we're integrating with respect to y, which means both our functions and our limits of integration have to be written in terms of y values. Okay, so the smallest y value that bounds the area is y is equal to c, so that's our lower limit. The biggest y value that bounds the area is y is equal to d, so that's our upper limit. And then we're taking the larger function, which is f of y, and subtracting the smaller function, which is g of y. Okay, so we're going to go through what we did in the previous example, but you're going to have to look at things differently here, where you're going to have to look at things in terms of y values instead. Okay, so if we work through the previous example, and we take both of those functions and solve those equations for x. When we solve our first equation for x, we get x is equal to y squared. When we solve the second equation for x, we get x is equal to y plus 2. Now the area that we're trying to compute is that same area that lies in the first quadrant. Okay, now this is how you're gonna have to change how you, okay? So up to this point, every problem that we've done, we've integrated with respect to the variable x, okay? And the way we've determined what function is the bigger function and what function is the smaller function is the larger function is the function that bounds the area from above. So that's going to be the function that lies on top. And the smaller function is going to be the function that bounds the area from below. So that's going to be the function that lies on bottom. Okay, when you integrate with respect to y, the larger function is going to be the function that bounds the area on the right-hand side, which is going to be the line that we have highlighted in yellow. And the smaller function is going to be the function that bounds the area on the left-hand side. So the function that bounds the area on the left-hand side is that curve. Okay, so what we're going to do now is we're going to set up an integral expression that is going to calculate the area of that region with respect to y. Okay, now we know we're going to be integrating with respect to the variable y, so our limits of integration have to be written in terms of y value. So when you look at that area, the smallest y value that bounds that area is the y value of 0. Okay, the line y is equal to 0, the x-axis, like that, like is the smallest y value that bounds the area. And the biggest y value that bounds the area is the y coordinate of the intersection point, which occurs at y is equal to 2. Okay, then we want to write the larger function minus the smaller function. So the larger function is going to be the function that bounds the area on the right-hand side, which is the line. Again, we have to write that function in terms of y, which is the line x is equal to y plus 2, minus, and then we're going to subtract the smaller function, which is the function that bounds the area on the left, which is the function x is equal to y squared. So we're going to write y squared there. And this gives us a much easier function to integrate. So we can go ahead and integrate this term by term. So the antiderivative of y is y squared over 2, plus the antiderivative of 2 is 2y, minus the antiderivative of y squared is y cubed over 3. And then we're going to evaluate that at our limits of integration 2 and 0. So when we plug in 2, we get 2 squared, which is 4, divided by 2 is 2, plus 2 times 2, which is 4, minus 2 cubed, which is 8 over 3. And then when we evaluate at 0, we get 0 plus 0 minus 0. So we get 6 minus 8 over 3, which is 18 over 3 minus 8 over 3, which we get that same area equal to 10 over 3. So again, when you compare that to what we did in the previous part, like we had to set up 2 different integrals to compute that area with respect to x. So how do we know whether we integrate with respect to x or with respect to y? I think mostly that's dictated by like how you have your equations written. So if you have your equations written as functions of x, then typically you're going to want to integrate with respect to x. If you have your equations written as functions of y, typically you're going to want to integrate with respect to y. But the one instance where that changes is if you have something like we have in this particular example, where either the function that bounds the area from above or the function that bounds the area from below changes at some point. And again, with this example here, the function that bounds the area from below changes at x is equal to 2. So when that occurs, a lot of times that's a good circumstance for you to integrate with respect to y. Makes things a little bit easier for you. It only makes it a little bit easier in this example, but in the next example we're going to look at, it makes things significantly easier. Okay, so the last example we're going to look at, the directions ask us to set up an integral that finds the area enclosed by the line y is equal to x minus 1 and the parabola y squared is equal to 2x plus 6. Okay, so what I want you guys to do for this is I want you to use your calculator to sketch a graph and then calculate the intersection points of those two curves. Like, I don't expect you guys to remember how to graph parabolas in the form like y squared is equal to 2x plus 6. So you can use your calculator for that. So again, use your calculator, draw the graph on your, like in your composition book, and then we'll talk about how to set this up together. Okay, so when you graph, you should have found the graph to look something like this. So that parabola y squared is equal to 2x plus 6 opens to the right. And again, the way that I remember this is if you have like y is equal to x squared, the graph opens up. Y is equal to negative x squared, the graph opens down. You have x is equal to y squared, the graph opens to the right. X is equal to negative y squared, the graph opens to the left. Okay, and then we also have the line y is equal to x minus 1. So graphically, that's going to look like this. Okay, and our two intersection points occur here at the ordered pair 5, 4, and they also occur over here at the ordered pair -1, -2. Now, if you had trouble graphing this, it probably has to do with that equation there, because in your graphing screen, you don't have like y squared is equal to something, you have y is equal to something. So if you wanted to graph this, you would have to like write two functions in the y is equal to screen. The first one would be the positive rad 2x plus 6, which would be what gives you the top half of the parabola that's opening to the right. And the second one would be y is equal to negative rad 2x plus 6, which is going to be the bottom half of that parabola opening to the right. Okay, so the area that we're being asked to calculate is the area here in black. Now, what we're going to do is we're going to just set up only like integral expressions in terms of x and in terms of y that is going to compute the area of that enclosed region. And there's one choice that is significantly easier. Okay, so the first thing we're going to do is we're going to set up an integral expression in terms of x. Now, when we look at things with respect to x, the function that bounds the area from above is always the positive radical. But when we look at the function that bounds the area from below, that changes. So the function that bounds the area from below on that interval in that highlighted yellow is going to be the negative rad 2x plus 6. And then from that point, red point going forward, the function that bounds the area from below is the one that's highlighted in blue. Okay, so we're actually going to have to set up two integrals to compute that area. The first integral is going to compute the area of the shaded region in green. And the second one is going to compute the area of that shaded region in black. Okay, so let's go ahead and set up both integrals. So the area here, if we want to compute the area in green, again, we're doing this with respect to x. So the smallest x value that encloses that area is -3. The biggest x value that encloses that area is -1. And then we're going to take the function that bounds the area from above, which is the positive rad 2x plus 6, minus the function that bounds the area from below. So the function that bounds the area from below is the one that's highlighted in yellow, which is going to be the negative rad 2x plus 6. We're integrating that with respect to x. Okay, so that's going to give us the area of that region in green. Okay, and then to that, we want to add the area of the region in black. So if we look at the x values that enclose that area, the smallest x value that encloses that area is -1. The biggest x value that encloses that area is 5. And then the function that bounds that area from above is the positive radical, so that's positive rad 2x plus 6, minus the function that bounds the area from below, so the function that bounds the area from below is the line y is equal to x minus 1. we're integrating that with respect to x as well. Okay, now if we wanted to actually go through and compute this by hand, I'm not going to do this because it's going to take a long time. But if you did want to do it, this would be how you would have to set it up. So the negative is going to change that to plus, both of those to plus. So really what we have is 2 rad 2x plus 6, which we're integrating with respect to x on the interval from -3 to -1. And if you wanted to evaluate that integral, you'd have to do a u substitution for that. So you would let u equal 2x plus 6 and work it from there. Okay, and then the second integral, like we would actually have to separate that into 2 integrals if we wanted to evaluate that by hand. So the first integral would be the integral from -1 to 5 of rad 2x plus 6, which we're integrating with respect to x. And I have to break it up that way because, again, I have to do a u substitution to evaluate that integral. And then we're going to subtract the integral from -1 to 5 of x minus 1, which we're integrating with respect to x. So again, that would be like a pretty brutal set of integrals for you to evaluate. You'd have to do 3 of them, 2 of which you would have to do by u substitution. So again, that's not the most efficient way for you to work this problem out. So again, even though both of these functions are y written in terms of x, because the function that bounds the area from below changes at some point, I actually think this is going to be a better candidate for us to integrate with respect to y here instead. Okay, so what I'm going to do to integrate with respect to y is I'm going to solve both of the equations for x. Okay, so when I solve the linear equation for x, we get x is equal to y plus 1. And then when I solve the quadratic equation for x, we would get y squared minus 6 equal to 2x. And then when I divide everything by 2, we get x equal to 1/2 y squared minus 3. Okay, so those are my 2 functions x written in terms of y. Okay, so if I want to set up an integral expression here, I want to integrate this with respect to y. So when I look at the smallest y value that encloses the area, that's the y coordinate of the intersection point down here. Okay, so the y coordinate of that point is -2. When I look at the biggest y value that encloses the area, that's the y coordinate of that intersection point up there, which is equal to 4. Okay, now I want to take the larger function minus the smaller function. So again, when we do this with respect to y, the larger function is the function that bounds the area on the right-hand side, which is the line, y plus 1, minus the smaller function is going to be the function that bounds the area on the left-hand side, which is going to be the parabola 1/2 y squared minus 3, which we're integrating with respect to y. And this is a super easy integral for us to evaluate. You would just have to distribute the negative across both terms, combine the constant terms, and then integrate that result term by term. I think when you do so both ways, like if you just want to check and practice, I think the value of that integral becomes 18 both ways. But it's definitely clear that when we integrate with respect to y, we get a much easier integral that we can evaluate. Okay, so make sure you guys have your calculators with you in class on Monday. I'm going to do a calculator lesson on Monday. I have a way to display. I had to spend like $165 on it, but I have a way to display the TI 84 calculator. So we're going to do a calculator lesson that'll give you everything that you need to know for your calculator currently. Okay, so we'll add some more calculator stuff on as we move through things, but This will teach you pretty much everything that you need to know on your calculator from this point. Okay, so hope you guys are having a great weekend, and we'll see you in class tomorrow. Take care.